Hello 20-1 students. So today we are looking at quadratic inequalities in one variable. So if you remember in our last lesson we were looking at linear equalities in one variable. So it's going to be a similar setup. We're going to have an equation for a line. In this case, that line is going to be a parabola, so it won't just be a straight line like we looked at last time. But we're still just working with the one variable. So we don't have y included yet as another variable. So just to kind of start thinking about how this is going to work, we have a sample graph here that we can work with and a quadratic function. So we have the inequality x squared minus 3x minus 4, and the inequality is that either the graph that's represented by this equation is going to be greater than 0 or it's going to be less than 0. So if we basically that equation has been graphed out here, and the first thing we want to do is just use the graph to identify the zeros of the function. So remember, the zeros or the roots are basically the x-intercepts. So we have 1 here at x equals -1, and we have 1 here at x being equal to +4. Now, the next point here mentions how the x-axis is divided into 3 sections by the parabola, and we want to know what the 3 sections are. Well, basically, for the x-axis, we have this first 0 and everything to the left of it, right, is kind of broken up by this line. So we could represent that as kind of saying that one section of this x-axis would be everything that is less than -1. So all the x values that are less than -1. Sorry guys, I'll just kind of bump that up a little bit. Then the next section that we have is kind of enclosed by our parabola. So we have values of x that are between the two zeros. So we could kind of say for that one that we have x is greater than -1, right? The values are going to be greater than -1, but they're also less than 4. And then, of course, for our last section, we have everything past there. So all the x values that are greater than 4. Okay, so the next thing we want to work on is identifying the x values for which the inequality x squared minus 3x minus 4 is greater than 0 is true. So basically, what parts of this parabola are above 0? So basically, 0 would kind of be like our like above our x-axis, or in other words, like 0 is kind of representing our y values. So if we're going above 0 here. So for which values of x is our parabola above the x-axis or at y values that are greater than 0? Well, it would be this section of the graph here and this section of the graph here. So let's maybe just highlight those. So for both of those sections, our graph is greater than 0. And so the x values for which that would be true would be any x value that is either at -1 or less. So this first inequality we looked at here. So x being less than -1. Or we have to skip over to the other side if we started at x being at 4 or greater, right? Although in this case we're not working with equal to, so we're just going to say when x is greater than 4, this parabola is above the x-axis. So we have 2 sets of values for x that will give us values for the parabola that are above the x-axis, or where the y values are greater than 0. Now the next one is asking us the opposite. For which values on this parabola do we have values that are going to be below the x-axis? So basically, where is the parabola below the x-axis? And of course that's going to be in this segment here. And so the values of x that are represented by this segment are this section here, right? It's from -1 to 4. So it'd be -1 x 4. So it's when x is greater than -1 and less than 4. So basically we figured that out, just by looking at which parts of the graph are above or below the x-axis, and then identifying the possible values of x for those. Now with this, the ones that are above, just keep in mind that we can say just generally less than -4 less than -1 or greater than 4, because we kind of have that, like if you think about what we've done with domain and range in the past, we know that this parabola can kind of keep going off into infinity, and so that means it's kind of like all possible values of x. So the only kind of restriction we need to put on it would be that it has to be less than that -1 if it's continuing to expand outward from there, or greater than 4. Okay. So we end up with kind of figuring out that we can write quadratic equations in the same way that we could with linear inequalities, in the sense that you can either have your graph of your quadratic function, so your parabola, either be like less than 0, less than or equal to 0, or greater than 0, or greater than or equal to 0. So those are kind of 4 possibilities. When we're trying to find solutions for quadratics, we can do it either graphically or algebraically. And when we're looking at our solution sets for our quadratic inequalities, we can either have no values that would provide a solution, one value, or an infinite number of values. Okay, so just keep in mind that there's multiple possibilities there. So let's look at one example here. Our first kind of examples are going to be fairly straightforward, where you have your whole quadratic on one side and it's always being compared to 0 on the other. So that's kind of a nice, easy way to get started, because you don't have to do any rearranging. So the first thing we want to look at is, what is this kind of telling us? Well, it's saying that our parabola here is going to be like the component that we're looking at in terms of this inequality is less than or equal to 0. So basically with less than, that means we're looking at the portion that is below the x-axis. Okay, so this is important to kind of determine when you're looking at solving graphically. Once we kind of can think about this, we want to, figure out how to graph the parabola. So we can easily do that just by factoring this one into to solve for the zeros. So if we look for two numbers that multiply to 16 and add to -10, that would be 8 and 2. So -8 plus -2 would give us -10. -8 times -2 would give us +16. So when we factor it, we're going to have x minus 8, x minus 2. And so what does that tell us about our x-intercepts? We're going to have one at x equals 8 and one at x equals 2. So now if we were to graph this out, let me just see here. We know we're going to be looking at positive values, so I'm going to set my graph up kind of to represent that. And then I'm going to do kind of like 1, 2, so we're going to have one at 2, 3, 4, 5, 6, 7, 8, and another at 8. And then, there's just going to be, the parabola is going to be, we have a positive x squared. So remember, that means that our parabola is going to open upwards. And I'm not going to really worry about too much else. I'm not going to worry about the vertex, because basically when we're solving, we're just trying to figure out if we graph kind of, however this is going to be kind of like that, let's say. We know it opens upwards. We know that it has an intercept at 2, 0 and 8, 0. Now, the only other part of the solution would be that we're figuring out which part of this graph is represented by this inequality, and we already figured out that it was below the x-axis. So essentially that would be this part right here. And so that tells us that basically our solution to this is that our values of x that are on the parabola have to be between these 2 points, right? Otherwise, if it would have been above the x-axis, we would have been looking for x values that were less than 2 or greater than 8, but because we're looking for between, we're going to be doing, and it's also greater than or equal to. Okay, so x has to be less than or equal to 8 and greater than or equal to 2 to fall between these ranges. So that would be our solution right there. Okay, so a little bit of a different kind of way of solving than with the linear inequalities where you were shading above or below. For this one, you're figuring out, you know, the parts of the parabola itself that are the x values for that part of the parabola that satisfy the inequality. Now we can also do this inequality. We can also do this algebraically by just basically solving for test points that would kind of be like if we've already done this factoring. We would essentially look at the different intervals, figure out any kind of a value of x that could satisfy the different parts of the inequality, and then put test points there. So like for example, we've already factored this, so we know that x could be equal to 8 or x could be equal to 2. So we want to look at ranges less than 2, between 2 and 8, and greater than 8. So even before we've done this, we kind of know that we want to look at that. So any x value less than 2, we could do 0. Between 2 and 8, I don't know, we could do 4. And greater than 8, let's make it 10, nice and easy. Once you have your points that, you know, fill in these kind of like spaces between the values that you've come up with from factoring, you can just substitute them into the equation. So we are going to have x squared. So in this case, we said x was 0 squared minus 10 times by x. So 10 times 0 plus 16. 0 minus 0 is 0, plus 16 leaves us with 16. And then the last thing we would want to do is figure out, is this thing that we've substituted in, so 0 when we substitute it into that equation, is it less than or equal to 0? So basically, is 16 less than or equal to 0? And it's not, so we would say that this is false, so not part of solution, or part of solution area. So basically we know that the graph, any part of the graph that's less than 2 is not part of the solution area. If we fill in the next one, we have, let's see, 4 squared minus 10 times by 4 plus 16, which would be 16 minus 40 plus 16. So let's see, 16 minus 40 plus 16 gives us negative 8. And so then we would say again, is negative 8 less than or equal to 0? Well, it is less than. And so we would say that this is true. So we know the part of the graph that falls between 2 and 8 is part of the solution area. And then for our last one, 10, I mean, usually once you've gone this far, you kind of know, because it's usually either these two or this part that are going to be part of the solution, but we can quickly plug it in. So 10 squared minus 10 times by 10 plus 16, which would give us 100 minus 100 is 0, plus 16 is 16. And just like we had there, 16 less than or equal to 0, it's false, so not part of solution. Okay, and so again, if we hadn't done the graph yet, we would just have, you know, looked at our factors and known that we had to be, you know, either less than 2, greater than 8, or between there. And, you know, we set up our chart of things that we're going to test based on that. We find that this part is true, so then we know that, you know, the middle part of the graph is going to be our solution area. So again, then you would just kind of say, like, this is our solution, although it should have been greater than or equal to there. Okay. Personally, for me, I don't know, I prefer just going through the graphic one. It just kind of makes more sense to me. But of course, you're welcome to do whichever method works for you. So in this next one, we have a negative x value. So we know that that means we're going to be looking at a different shape of graph. It's going to be opening downwards this time. And so again, we want to factor it. Before we do that, again, just looking at this, we're saying that our graph is less than 0. So that means it's going to be below the x-axis is where we're going to find our solution. X-axis. There we go. Okay, so factoring, we want to take out the negative to start. So if we factor out -1, it's going to be x squared. Factoring -1 out of positive 3x gives us -3x, and then out of positive 10 gives us -10. Two numbers that multiply to -10 and add to -3 would be 5 and 2. X, but it would have to be -5, and it would have to be positive 2. So -5 plus 2 gives us -3. -5 times by positive 2 gives us -10. So now we have our solutions of x being equal to 5 or x being equal to -2. Because remember, these, we're just basically setting this whole thing equal to 0 when we're doing our solutions. So that's, where we're getting our roots from there. So now if we wanted to put this into a graph really quickly, again, don't worry too much about the specifics for these. We know that our graph is going to be between, oh shoot, I wasn't really paying attention to the numbers there. There we go. Okay, so let's say, I'll try and keep it somewhat 1, 2, so this is going to be -2. And what do we have? 5, 1, 2, 3, 4, 5. Okay, so 5, 0, and -2, 0. And we said that we have a negative a value, so that means that our graph is going to open downwards. So again, don't worry too much about the vertex and stuff like that, but just kind of sketch out your parabola. It always falls apart on the second side, whatever. And we said our solution area was going to be below the x-axis. So basically that means this part here and that part there. And so what that tells us is that our x values that are going to be solutions are going to be the ones that go less than -2 and greater than 5. And we're just working with less than, not the equal to, so we would just say x. Oh, you know what? We don't want to write it like that because we're not between 2 points. So sorry, the solution would be x is less than -2 and x is greater than 5. Okay, so there's our solution. Maybe you can see why I like graphically. I feel like it's really quick and easy. If we want to solve algebraically, again, we just figure out our test points. So for this one, again, we had our factoring of 5 and -2. So we would say, what's an x value less than -2? I picked -5. What's between -2 and 5 would be 0. Above +5 would be 10, for example. I mean, you can choose any value. I'm just choosing kind of whatever, I guess multiples of 5. So then we just want to plug those in. So -5 squared plus 3 times -5 plus 10. So -5 squared is 25, but again, we have that negative in front of it. So -25 plus 3 times -5 is -15 plus 10. And so when we do that, we end up with -30. And our inequality is that our x value should be less than -2. And -30 is less than -2, so this is true. So we know that this would be part of our solution area, every value of x that's less than -2. For this one, we have 0, so it's going to be -0 squared plus 3 times 0 plus 10. So basically plus 10. And so our inequality is saying 10, oh, oops. Our inequality is saying that -2, 10, 5. So we're saying basically 10 is between 5 and -2, which is false. And so that means that it's not part of the solution area, not solution. And then just like I mentioned, basically once you've done these two, you always know the last one, but we'll do it anyway. So we have -10 squared plus 3 times by 10 plus 10. So that would be -100 plus 30 plus 10. So basically -100 plus 40 gives us -60. And is that greater than 5? Oh. Sorry guys, I totally just realized I've been putting in my values here and I should be using the one from the actual inequality. So really what I should have had here is -30 is less than 0 is what we're comparing to. This is just our ranges that we're looking at. And then again here, so for, we got 10 for this one, so the inequality was that it was less than 0, which is still false. And then for this one, it'd be -60 is, again, less than 0. So don't make my mistake and start using these inequalities. This is why I hate the algebraic method. I don't know, I just don't like it. So then again, -60 is less than 0, so it's true, so it's part of the solution area. So again, we end up with this same thing, right? We would say basically our inequality is this one and this one that we've set up. Okay, let's try one more example. I'll try to do better on the algebraic component this time. So in this example, we have a bit of a different setup, right? We have x squared minus 4x is greater than 10. So usually what we want to do with this is rearrange the equation so that we have a 0 on this side, just the way we did with the other ones. So like x squared minus 4x greater than 10, we want to do -10 minus 10, and that's going to give us, oops, x squared minus 4x minus 10 is greater than 0. Okay, so now that kind of allows us to do more easy factoring and things like that, and to solve for our zeros. Now for this particular one, if we're thinking about numbers that multiply to make 10 and add to 4, there actually isn't any. And so if you can't factor it like pretty easily when you first see it, you can use your calculator. So for this one, I would go into, you go to y equals, and you're going to put in, let's see, x squared minus 4x minus 10. And you know, for any of the ones, like even the ones that you would have factored, in like a test, you would probably be asked to show your factoring, but you can still put it into your calculator and check it against your solution just to make sure that you're on the right track. Okay, so we have our graph here. So remember, what you're looking for is your x-intercepts, of course, or your zeros. So in order to solve for that, remember you're always going to be pressing, sorry, this camera always has like the worst reflection, but I want you guys to see the buttons. So second function, trace, and we're looking for the zeros, so enter. Or just like scroll down and hit enter there. Now remember, it's always going to ask you left bound, so you want to make sure that your cursor scroll like left or right so that you're to the left of whatever x-intercept you're looking at. Then it'll ask you right bound, so make sure you're just to the right of that x-intercept on the parabola. And then it'll ask you guess, so hit enter one more time, and we see that we end up with x is equal to -1.74. And our other one, second function trace, 0. And so again, it's asking you for left bound, so just kind of like scroll over so that you're closer to the second intercept, but it's still to the left on the parabola. hit enter, and then it'll ask you right bound, so go to the right of the x-axis, or of the x-intercept, and then hit enter again. So it tells us our 0 is at 5.74. Okay, and so, you know, if we want, we can just kind of do like a quick little sketch again. And if you were asked to solve graphically on a test, you would make sure that, like you would want to make sure that you did do a little bit of a sketch. So 1.74 would be kind of like right around there, negative 1.74, and 1, 2, 3, 4, 5.74 would be kind of right around there. Don't forget, if you have written questions like that, make sure, I know lots of you guys always forget, so make sure that you, when you're finished with a written question, you email it to me, like when you're finished with the test, right? So you take a picture and send it to me, as well as showing it to the cameras. Okay, so now we can sketch. We had a positive x value, so that means it's going to be opening upwards. I mean, I guess we saw that on the graph anyways, but my graph kind of went off screen, so I'm just going to kind of go like that. Okay, so those are my values, and remember, for our inequality, we said that this is greater than 0, so that means it's going to be above our x-axis, so the components of our graph that are a solution would be here and here. So what does that mean? Well, our 0 here was negative 1.74 comma 0, and this one was 5.74 comma 0. So our inequality would be that we have to have values that are less than negative 1.74 or greater than 5.74. So x is less than negative 1.74, and x is greater than 5.74. So that's my solution there. Now, I told you guys I'd try to do better on the algebraic one, so let's see how that works. So the first one I'm looking at is, right, I've solved for my zeros, so I'm always going to set up my algebraic test to be less than the lowest number, between the two numbers, and greater than the largest number or the highest number. And then we just find test points that are, you know, within those ranges. So less than negative 1.74, I chose negative 5, between was 0, and again above was 10. So if we put that in, I would recommend that when you're putting in your test point, use the original version. Now this is going to make it a little bit weirder because you aren't comparing to the 0 the way you would here, but if you made an error with your like with moving things around here, it won't be affected by this. So that's why I recommend using the original one. So basically x squared minus 4x. So if we're using negative 5 squared minus 4 times by negative 5 is greater than 10 is what we're trying to say. So negative 5 squared is 25. Minus 4 times negative 5 is negative 20, so minus negative 20 is plus 20, and greater than 10. So 25 plus 20 gives us 45, which it satisfies that inequality, so it is greater than 10, and so we would say that's true, so that means it's part of the solution area. For the range in between, we would have 0, so 0 squared minus 4 times 0 should be greater than 10. And that's basically just 0 is greater than 10, and 0 greater than 10 is false, so it's not part of the solution area. And then our last one is 10, so 10 squared minus 4 times 10 is greater than 10. So 100 minus 40 gives us 60, which is greater than 10. So that satisfies our inequality. So we would say true. And so now we would just look at our setup that we have here are less than and are greater than are true. So we would write those as our inequality, just the way we did for our graphical one. And so that's our solution. Okay, so you guys have one to try on your own, so maybe pause the video and see if you can do this. Try both methods just so that you're comfortable with each one of them. And then when you're finished with that, you can unpause the video and we'll just go through a really quick word example together before we wrap up the lesson. So in this one it says, suppose a baseball is thrown from a height of 1.5 meters, and then we're given, you know, kind of like a complex inequality, models the time that the baseball is in flight. During what time interval is the baseball in flight? So, you know, with something like this, that's, you know, pretty complex, like all these decimals and stuff. We're just going to use our graphing calculator to make things nice and easy. So all right, so I just sketched out the basics there so you guys don't have to wait for me. So just going into your graphing calculator, entering in your, you know, the equation for the parabola, so negative 4.9 x squared plus 17x plus 1.5. And then when we go to our graph, if you're using the standard window settings is fine. I did modify it just so that you guys could see it a little bit more easily what was going on. But you will be able to see what you need to see with the standard window settings. You won't see the vertex, but we don't actually worry too much about that for this one. So just kind of keeping in mind what are our zeros. So second function trace, 0, and it's asking you for the left bound. So maybe let's go over to this one. Okay, left bound, enter, right bound, enter. Guess. And so we see that our 0 is, x would be negative 0.08 when y is 0. So keep in mind with our inequality, the x variable is actually t, time. So if we have negative 0.08 as our time, does that seem like it would fit into a real life situation? Well, no, we should never have a negative value for time. And in fact, we were told that the ball was thrown from a height of 1.5 meters. At this point, the height is 0. And so that's why we have the negative time, because that's not actually representing where the ball was when it was lifted off, kind of. So if we wanted to, what we could do is go to second function trace and go to 0. And what we want to find is, or sorry, now I'm stuck on that. We want to go to, sorry, number 1 value. And that allows us to just enter our x value. So what we want is where was the ball at time 0. So x is 0. And we see that just like we would expect, the height of the ball was at 1.5 meters, right? So that's where the ball leaves from. Then going from there, it's asking you what time interval is the baseball in flight. So we want to think about if the time started here at 0, what would it be the time where it, or what would we see on the graph when the flight ends? Well, we would expect that the ball goes like, you know, it flies up in an arc and then it lands, like we're going to assume it doesn't get caught, right? We're making some assumptions there. So basically when it's at ground height is where it ends. So our x value when it's at ground height is the time where it lands. So we're going to go second function trace and go to 0. And so again, we're going to go way over to the left side here, left of our x-intercept and then right of our x-intercept and then guess. So it says that our 0 is x equals 3.55, so 3.55 when y is equal to 0. Okay, so basically what we're seeing here is that the ball is going like, no, I didn't maybe scale this the very best. But kind of like that, right? So when it asks us for the time interval, just make sure that you're looking for the difference in time from like 0 to when it lands, not from the other x-intercept to this final x-intercept, which is a common mistake that students make. They forget to account for the reality of the situation. So basically, if we went from 0 to 3.55, that means that the ball was in flight for 3.55 seconds. So we could say t was greater than 0 and less than 3.55. And of course, on a test and a written question, you would write out that verbal answer I just mentioned as well, too, that the baseball was in flight for 3.55 seconds. Make sure you use the units that are given. Okay, so that's everything for quadratic inequalities in one variable. So you guys have an assignment to work on from the textbook there, and be sure to check your solutions against the textbook solutions that are provided on the web page. And next time we're going to start on to lesson 9.3, which is quadratic inequalities in two variables, and we're actually going to break that lesson into two parts. So 2 more lessons left in the unit. So I will see you then.